Hello everybody. Today we will be looking at question number 26 to question number 30 of the JAM 2020 chemistry question paper. Moving to question number 26, the rate of solvolysis of compound 1 to 4 follows. So there are four compounds which are given, four cyclic compounds, and we have been asked to arrange these four compounds in the order of decreasing rate of solvolysis. So we have to arrange these four compounds in the order of decreasing rate of solvolysis. So which of these compounds will show the least rate of solvolysis, or which of this compound will show the most rate of solvolysis? Now solvolysis is basically just a reaction of this cyclic compounds with a solvent molecule. The solvent can be water, alcohol, etc. So basically solvolysis can be considered as a substitution reaction, a nucleophilic substitution reaction, an SN2 reaction where the solvent is acting as a nucleophile. So just as in the case of a SN2 substitution reaction, the solvent will try to replace the nucleophile, in this case which is the bromide. And so the first step in this SN2 nucleophilic substitution would be the generation of the carbocation, and which will also be the rate determining step. So the more stable the carbocation is, the more will be the rate of solvolysis. The carbocations generated, the more stable the carbocation is, the higher will be the rate of solvolysis. So basically in this question we have to find which are the most stable carbocations. The compounds which give the most stable carbocations will show a higher rate of solvolysis. Now looking at these four compounds, compound 3, if you look at the carbocation right here, which is generated by compound 3, it is actually an aromatic compound. The carbocation is actually aromatic because it obeys the Huckel's rule. There is 2 pi electrons, so it obeys the 4n plus 2 pi electrons. It's a cyclic planar system. This is an sp2 hybridized carbon. The carbocation carbon is a sp2 hybridized carbon, and these two carbons are also sp2 hybridized. So we have a nice 3 planar cyclic ring system with 2 pi electrons. So it obeys the Huckel's rule. So this is an aromatic compound. So this carbocation is really stable. And if you look at compound 4, the carbocation generated from compound 4, this is actually an anti-aromatic system. Here also we have a cyclic system, a cyclic planar system. We have 5 carbon atoms on a plane, almost a plane. This carbocation carbon is sp2 hybridized, and all these carbons are sp2 hybridized, and it has 4 pi electrons. So when you have a 4 electrons system with 4 pi electrons, it is anti-aromatic. So this is anti-aromatic. So this is a highly unstable carbocation. So this compound 3 carbocation will have the highest rate of solvolysis, and compound 4 carbocation will have the least rate of solvolysis. So either B or C is the correct answer. Now we have to decide whether which one or 2 has the highest rate of solvolysis. If you look at 1, the carbocation generated from 1, you have a carbocation at the bridgehead position. The carbocation is at the bridgehead. Now this is a very unstable position. So this carbocation is unstable, whereas compared to carbocation generated from compound 2. See, in compound 2, the carbocation is actually resonance stabilized. This pi electron system can shift here to over here, and you will have the double bond here, and the carbocation positive charge can move to this carbon. So you see this carbocation generated is a resonance stabilized carbocation. So compared to 1, 2 is more stable. So option C will be our correct answer. Option C is the right answer. Moving to question number 27. The more stable species in each pair of conformers are. We have 3 pairs. 3 pairs are given, 3 pairs of conformers, and in this we have to find in each pair which is the most stable species. So let's look at one pair at a time. Let's look at the first pair. Here we have a cyclohexane system, and here we see that the tertiary butyl group is on the equatorial position. This is the bulky group which we have on the equatorial position, whereas in this conformer we have the bulky tertiary group on the axial position. Now, when we have the bulky tertiary butyl group on the equatorial position, we find that, like in this case here the bulky tertiary butyl group is on the equatorial position. There is no axial interactions because it cannot interact, as it is on the equatorial position, it cannot interact with any of the axial hydrogens. But when this when this equatorial this tertiary butyl group here comes on to the axial position, here we can see that it can actually interact with the hydrogen here, the hydrogen which is here on the axial position. So this tertiary butyl group can have a 1,3 diaxial interaction with this hydrogen over here on the axial position. So here it will have that steric interference, steric hindrance. So over here there is no steric hindrance as the tertiary bulky tertiary butyl group is on the equatorial position. There is no such 1,3 diaxial interactions. So this is more stable. This is not as stable as this because here we have steric issues. There is 1,3 diaxial interactions. Now let's look at the second pair. Second pair you see again, let's see where we have diaxial interactions. Right here, see the methyl and the hydrogen, they can have a diaxial interaction. This methyl right here and here. The bulky tertiary group is on the equatorial position, so it cannot get involved in any diaxial interactions. 1,3 diaxial interactions. Over here, let's look at this pair, this compound here. Again, we see the tertiary butyl group is right here in the axial position, but now there is no hydrogen here in the axial position. So there is no hydrogen, so there is no possibility of a 1,3 diaxial interaction. So here we saw a 1,3 diaxial interaction, but no such 1,3 diaxial interactions in this case. So this compound 4 is more stable. Now again, let's look at the last pair with the OH group. Now right here, the OH group, which is on the axial position, actually it can hydrogen bond to this oxygen. So if the hydrogen comes around here, the hydrogen can actually involve in a hydrogen bonding with this oxygen. But here the OH group is in the equatorial position, so there are no chances of the OH involving in any type of hydrogen bonding with any of the oxygen atoms here, as this OH is in the equatorial position. So here this compound with the hydrogen bonding is more stable because the hydrogen bonding, intramolecular hydrogen bonding, makes it more stable. So here the equatorial bulky group compound 1 is more stable, here compound 4 is more stable, and compound 5 is more stable here. So solution B is the right answer here, solution B. Moving on to question number 28. The major product formed in the following reaction sequences. So we have a reactant and two reagents are given. So the reagent, first reagent is a titanium chloride and copper zinc mixture. So when you look at this, immediately you have to remember that this reagent is a McMurray reaction reagent. A McMurray reaction is when an aldehyde or ketone undergoes coupling with each other to form an olefin. For example, an example is shown here. Here the ketone is coupling with itself. So two of these molecules will couple with itself and it will form the double bond right here. So this two molecules coupling to form a double bond right here where the ketone was. So this is what a McMurray reaction is. And the reagent for this reaction is titanium chloride or titanium tetrachloride together with a reducing agent. The reducing agent here is copper zinc. Sometimes you will also see lithium aluminum hydride here. In the original McMurray reaction, lithium aluminum hydride was the reducing agent. So either if you see lithium aluminum hydride or copper zinc together with titanium chloride, remember it is a McMurray reaction happening if the reactant is an aldehyde or a ketone. So the first step, we did the McMurray reaction. So we get here is the keto group, C double bond O, the aldehyde group, C double bond O. It will couple with itself. The two of these molecules will couple with itself, and here we'll get the new double bond which is being formed by the coupling of these two reactants. So this is the new product formed after the McMurray coupling reaction. Now the second reagent here is HCl, acid. It's basically an acid hydrolysis which is happening here. So the second step is a step for acid hydrolysis. So basically this enol ether will get hydrolyzed. So when you have an enol ether, it will hydrolyze to a ketone. Okay, so this enol ether group right here and right here, we have two of them. They both of them will get hydrolyzed to a keto group. Now, if you want to know more about the mechanism of this hydrolysis of the enol ether, I have it here for you. See, when you have an enol ether and when you do acid hydrolysis on the enol ether, the first step is the double bond here. It will take up a proton and you will get this saturated. You will saturate this double bond, and the lone pair on the oxygen moves here, and you will get this double bond here with a positive charge on the oxygen. The second step is the water attacking this slightly positive carbon here. Water attacks here through its lone pair of on the oxygen. It attacks on this carbon, and as it attacks here, the oxygen, the double bond O, the pi electron goes back to the oxygen as lone pairs. So here you will see this, and then the next step is a base will abstract one of the proton from this water which is bonded to this carbon. It will abstract a proton, and you will get the OH here. You will get a compound like this. You will get a compound like this, and the final step is the proton, the oxygen, the lone pair of this oxygen will attack acid group, a proton here, and it will form the OH bond and the positive charge on the oxygen, because it has used the lone pair on the lone pair on the oxygen to form this bond. And finally this bond will break, it will go back to the oxygen, and methanol is released, and basically you will end up with a ketone. So this is the mechanism, just in case if you want to know what's happening here. But always remember the hydrolysis of enol ether, double bond, carbon carbon double bond with an ether group. If you have an enol ether which is undergoing an acid hydrolysis, you will end up with a keto group. Okay, so next, moving on to question number 29. For the Diels-Alder reaction 1 to 4, the activation barrier follow the order. So 4 Diels-Alder reaction is shown. There are 4 reactions, Diels-Alder reaction. In which case the dienophile is the same. For all the 4 reactions, we have the same dienophile, which is this. And the diene is changing. For the first reaction, it's a cyclopentadiene. For the second reaction, we have the furan. For the third reaction, we have the thiophene. And for the fourth reaction, we have the pyrrole system. So the dienophile is the same, but the diene is different for these 4 Diels-Alder reaction. So now, which will be having the highest activation barrier, and which has the lowest activation barrier for this? So basically for that, all we have to look at which of these dienes are more stable. The diene which is more stable will have less reactivity and will have a high activation barrier, because it will show difficulty in reacting because it is very stable. So we have to find which of these dienes are more stable. So if you look at this, if you look at the cyclopentadiene, this first one, this is not an aromatic system. The remaining 3, which is the furan, the thiophene and the pyrrole, they are all 3 are aromatic, which means they are more stable. But this cyclopentadiene is not an aromatic system. Here you see 4 carbons is sp2 hybridized, and the 5th carbon here, it's an sp3 hybridized carbon. So the structure is like an envelope. This carbon is slightly raised from the plane of the other 4 carbons. So it is not an aromatic system, it's not a planar system. So it is not very stable compared to these 3. So that means it will be more reactive, because it is no stable, it will show a tendency to react, and therefore the activation barrier for this will be the least. So one will have the least activation barrier and the highest reactivity. So it's C or option D is the correct answer, because in both of these the activation barrier for one is the least. That means the activation barrier is the least for one. That means the reactivity is the highest for one. So which one is this, C or D? Now out of the remaining 3 Diels-Alder dienes, we have to find which of these aromatic system is more stable. that is whether the furan or the thiophene or the pyrrole, which of the three, we have to arrange them in the order of their aromatic character. Now if you look at these three, uh, if you look at oxygen, oxygen is the most electronegative element when you compare it to nitrogen and sulfur. Now to make this system aromatic, oxygen actually has to donate one of its lone pairs to this pi electron system to make it a 6 pi electron system and aromatic. So oxygen, because it is most electronegative out of these three, it will have a less tendency to share its electron. It will not like to share its electron. So the less aromatic character out of these three is for actually the furan ring system, the furan ring system. Thiophene, which is actually the least electronegative of these three, it will show a tendency to share its lone pair of electrons. So it will love to share its electrons to donate to make the 6 pi electrons, and so this is showing more aromatic character, whereas pyrrole is in between these two, because the electronegative nature of nitrogen is between oxygen and sulfur. So the most aromatic is, of course, the furan. So because it is the least aromatic is furan, and because it is showing less aromatic character, it is less stable. It is less stable, and so it can easily react, and it will show less activation barrier. So 2 will show a less activation barrier than compared to 4, which will show a less activation barrier than compared to 3, because thiophene is the most stable of all these 4. Thiophene is the most stable, it's most aromatic, and therefore it will because it is most stable, it will show a less tendency to react, and therefore it will show a higher activation barrier. So option C here is the correct answer, option C. Moving on to question number 30. The major product formed in the following reaction is. Now this is a iodolactonation reaction. So you see a cyclic 6-membered cyclic system, which is being with a carboxylic acid group here, and it is being reacted with iodine and a base, sodium bicarbonate. So this is an example of an iodolactonization reaction. So first of all, the base, sodium bicarbonate, will abstract a proton from the carboxylic acid group here, as in here, and it will form the carboxylate anion. Now the second step is where the reagent iodine attacks this double bond. Now this iodine can attack the double bond either from below this cyclic system, or from above the system, and accordingly it will have two stereo positions. So here the iodine is above this plane, and this iodine here is below, attacking from below. So the iodocation is below this system, and here it is coming out of the plane. And here you see the carboxylate is also out of the plane. Here it is facing, it's coming towards us here, this carboxylate group. Now if this carboxylate oxygen, this oxygen has to attack this carbon here, it cannot come from above the plane, because here we have the bulky iodine is sitting on top here. So this oxygen cannot come here and attack this iodine here. But here, because the iodine is below, it is away from the from us, and it is away from this oxygen, this now can attack right here. So this is remember, this is facing towards us, and here iodine is away from us. So now because iodine is away, the oxygen which is also towards us, now it can attack this carbon here, and so that's why it attacks this carbon here and forms a bond like this. And the iodine, this bond breaks, and iodine, we get an iodine here facing away from us. Okay, so basically if you look at this, this and this makes no sense. C and D makes no sense absolutely, because here you have one, the oxygen bond is facing up, facing away from us. Here it is facing towards us, so it doesn't make sense, this too. So this too looks okay, but in this too, B is the correct option, because here B, the iodine is facing away from us, and so this oxygen of the carboxylate group, which is facing towards us, can attack from the front side. It can attack this carbon. because it now here doesn't have to feel the steric hindrance from this iodine. But if it was here, here you see it cannot attack from the front side, because in the front side the iodine is sitting here, so it has steric hindrance here, so the carbon cannot attack from the front side here. But since here the iodine is sitting away from us, is faced away from us, the carbon now can attack from the front here. So option B is the correct answer here. Okay, so thank you very much.